Hello class, welcome to this video on the 4.4 conditional probability and independence. So our learning goals today are to find and interpret conditional probabilities using two-way tables, use a formula for conditional probability to calculate probabilities, and determine whether two events are independent. All right, so as far as today's lesson goes, our question today is how do we calculate conditional probabilities and determine whether given events are independent? So looking at our first example, we have here a survey conducted on males and females and on whether they pierced their ears or whether they did not pierce their ears. So here for number one, if we know that a randomly selected student has a pierced ear, what is the probability that the student is male? So if we know that we're looking at a student with a pierced ear, which means we're looking at this row here. So if we focus on this row, how many students have pierced ears? In this case, we have 103 with pierced ears. And so therefore, we're going to say, and then out of those 103 with pierced ears, what is the probability that we get a male? And that's going to be 19. So it's going to be 19 out of 103. And that probability is going to be equal to, should be 0.184. All right, so the next one, if we know that a randomly selected student is male, so if we know that they're male, so we're looking at this male column. If we know that they're male, well, there's 90 males. What's the probability that the student has a pierced ear? So then there's 19 out of those. So it's going to be 19 out of 90. And this is 0.211. All right, so notice that number 1 and number 2 sound alike, but they actually aren't. In fact, the probabilities aren't even the same. So these probabilities are known as conditional probabilities. So they're actually different probabilities, right? So we're going to go ahead and define what a conditional probability is. And it's sort of in the name. So a conditional probability essentially imposes a specific condition. In this case, the condition is if we know that they have a pierced ear. So that's my condition, is that given that pierced ear, what is the probability that they're male? And then number 2, the condition was that they have to be male. So in this case, the conditional probability is the probability that one event happens given, I'm going to underline that, given that another event has happened. So the condition here is that there's an event that already has happened. Given that that has happened, that condition, what's the probability of a specific event happening? And we usually denote this with a bar. So in general, it's P of A given bar, right? A or A given B. So that's how you pronounce this, A given B. That's how you pronounce that part. And so in general, we know that it's not equal to the probability of B given A. So, and this is, again, this is B given A, the probability of B given A. And we know it's not necessarily equal to. Why? Because we did that here. In this example, the probability that they have a pierced ear, or that given that they have a pierced ear that they're male, and then we reverse it, it's not the same probability, right? So calculating conditional probabilities. Okay, so looking at the example that we did, let's kind of re-emphasize this. It's the probability of male given pierced ear. Pierced ear is the E, event E. And we said that that was 19 over 103. And that was equal to 0.184, right? And another way to consider this problem is to think of it like this. The probability of male given pierced ear can be also calculated by looking at just the probability of, in this case, males, 19 out of 178. You just look at the males. And then you divide that by the probability. Well, not just male. I guess I should be more specific. The probability of males and they said yes, right? So it has to be both put together, both events. So that's males that said yes, so 19 out of 178, divided by the probability of someone with a pierced ear. So in this case, 103 out of 178. Now, if we do that, then these will cancel out, giving me the same probability that I had earlier. So we know that these will kind of cancel out, right? And that will give me the exact same probability. Now, notice that this was the probability. The top was the probability that it was a male and they had a pierced ear, right? Over the probability of pierced ear. In other words, it was the probability of male and pierced ear divided by the probability that they had a pierced ear. And that's essentially the formula we're going to talk about. The formula for conditional probabilities. Given events A and B, the probability of A given B is the probability of the conjunction of the two events A and B divided by the probability of the given event. And then the probability of B given A is the probability of the conjunction of events B and A divided by the probability of the given event. So those are the formulas, and you can kind of see that that's related to what we wrote on top. Now, the quick tip for calculating is that the conditional probability is the probability of both events occurring. So the probability that they both occur on the top over the probability that the given event occurs. Okay, so it's the probability of both divided by the probability of the given event. And that's how you calculate the conditional. If you remember that little tip, you should be able to calculate any conditional. All right, so let's look at the another example. So we have a survey done on those that are part of an environmental club, and we wanted to see if there's a relationship between those that were in an environmental club and whether or not they used, rented, or never used, rented, or owned a snowmobile. All right, so what's the probability of randomly selecting someone who is not in an environmental club, given that they have rented a snowmobile? So we have the probability. So we're going to go ahead and name these here. The event E is that they are in an environmental club. I'm just going to shorten it here. And event R is that they are a renter. I'm just going to say they are a renter. Okay. So in this case, the probability that they are not in an environmental club, given that they have rented a snowmobile. So like we said earlier, we can calculate this by saying the probability that they both happen, right? Divided by the probability that they rent, right? You could do that, of course. And if you did that, you would get the same answer as what we're going to get now. Okay, I'm just gonna get the answer right off the bat. All right, so you can use a two-way table for that. So you want the probability that given snowmobile, given that they rented, so given this guy, that's in the denominator. Given that, how many people were not in a club? Well, it's these guys, right? So given these renters, 497 were not. And that's your probability. Okay, so that's going to be 0.866. Now, if you use this formula, it would end up being, if you were to use this formula, it would be 497 out of 1526 divided by 574 over 1526. But then you would notice that the 1526 will cancel, leaving you with what we just got here. All right, so for part B, what is the probability of randomly selecting someone who has rented given that they are not in an environmental club. And if you have the notes, I crossed this out. It says not rented, but it should say rented. All right, so the probability that they rented given that they're not. So notice it's the reverse of that. So in this case, we want the probability that they rented and they were not in a club divided by the probability that they are not in a club. And again, we're just using a two-way table for this. So they rented. So we're just looking at the not environmental clubs, these guys. So these guys, out of these guys, how many also rented? Well, in this case, it's 497. All right, and then that's going to be 0.407. And notice that these probabilities are not the same. So in general, these are not going to be the same, right? So I'm going to go ahead and back in our notes here, I'm going to say that these are not, let's see here, in general. So let's see here, where was it? Should have been over here, calculating conditional probabilities. So in general, I'm just going to highlight that. In general, they're not equal to. So I'm going to put in here that this is not equal to this in general, okay? All right. So when is it equal? Well, it's equal when the events are independent. So we're going to look at this here, conditional probability and independence. So example 3, suppose we toss a coin twice. The event A, first toss is a head. Event B, second toss is a head. So what's the probability of the second toss being a head, given that the first toss is a head? So the probability that the second toss is a head, so that means A, the probability of A. In fact, I'm going to actually, let's see. Yeah, just leave it like that. So first toss is a head, given that or a second toss is a head, given that the first toss is a head. Okay, so probability of B given A. Well, in this case, if you were to do the probability of both, right, divided by the probability of the given, you would get, well, okay, so if we have a 2-coin toss experiment, you can get heads, 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 tails, tails, heads, and then tails, tails, right? So the probability of A given B, well, that's heads and heads. Well, that's only 1/4. And the probability of getting heads is a half. So 1/4 divided by a half is 1/2. All right, and again, if you forget how to do that, remember 1/4 divided by 1/2, you use KCF, keep change to multiplication, and then flip this to 2/1. And then that's going to be 2/4, which is a half. Okay, just to remind you. But we know that it's going to be a half. Does it matter that the first toss is a head? No, we know that the second toss is also going to be probability of 1/2 for it to be heads. But I just wanted to show you the formula. Now, what's the probability of the second toss being head, given that the first toss is not a head? So A prime, right? A prime meaning it's tails, right? So the probability of B and A prime, I'm going to try to keep the consistent here, B and A. And I'm going to say B and A prime. I just like to do the order the same. And then probability of A prime. So we know it's the same thing. So we want tails and then heads, right? Well, there's only one way to do that, and that's this guy. Tails, the first toss is tails, the second toss is heads. So that's still going to be 1/4 divided by the probability of 1/2, which is the probability of tails, which is still going to be a half. So we know that when we reverse this, the probability is going to be the same. So for the above example, we've noted that the probability of B given A is equal to the probability of B. Okay, so I'm going to say that this is equal to the probability of B. Okay. Okay, actually what I'm going to say is it's equal to the probability of B. So I'm going to say that this is equal to the probability of B, and this is also equal to the probability of B. The probability of B is that there's a probability of heads, right? So this is equal to the probability of B given A prime as well. They're equal to each other. And they're also equal to, in which they're equal to the probability of B. There should not be a blank there, so we can cross that out in your notes. So we note that this is the case, that this is true, which means that knowing whether or not the first toss is a head does not change the probability that the second toss is a head. So it doesn't matter whether it's A or A prime, it's still going to be the probability of B. B is still going to happen the same number of times, or the same probability. So events A and B in this case are known as independent events. So what's the definition of an independent event? Okay, so the definition of independent event is an event where knowing whether or not one event has occurred doesn't change the probability that another event will occur, right? So it's events in which knowing whether or not one event has occurred does not change probability that the other event will happen. Okay, so whether or not the event happens does not have any impact on whether a specific event is going to happen, the probability. All right, that's known as independence. So what are the ways of determining if things are independent? Well, the way to do it is if the probability of A given B is the same thing as the probability of A given B prime, whether or not B occurs, it's still going to be the probability of A, right? A is not going to change just because it was given that B did or did not happen. And the probability of B given A should be the same thing as the probability of B given A not happening, because it doesn't matter whether A happened or not. It's still not going to have any impact on the probability of B, if that makes any sense. So that only occurs if they're independent. All right, so let's take a look. How do we determine if two events are independent again? Let's go ahead and look at this example, the same one that we did before. So let's look at male versus, is there a relationship between male, whether it's male or female, and whether they pierce their ear or not? From experience, you would say yes, there is a relationship between those two, but let's go ahead and calculate it. So let's do a method 1. So 2 ways that you could do it. You could do it by doing this method, or you can do it from this method, right? Because these all have to be the same at the end of the day. Okay, so method 1, we're going to use this method to see if those probabilities are going to be the same. So let's go ahead and say, let's use a male and then pierced ear. So what's the probability of male given, let's change this to M for male, just to make it easier. Probability of male given pierced ear. So the probability of male given pierced ear, we did that earlier, is 19 over 103. And again, that was from given that they said yes to the pierced ear. What's the probability that they're male? So 19 out of 103. And then the probability of male given not pierced ear. So let's look at the not pierced ear. Well, that's 75. Out of those people, 71 were male. And then 0.947. So look at that. 95% of the males, higher chance of selecting a male if you're looking at people without pierced ears. If you're looking at people with pierced ears, that probability drops, right? So there is a relationship between whether or not they pierced their ears and the gender. Okay, so there's a relationship there. So let's talk about method 2. The probability of male given pierced ear is 0.184. We did that earlier. We did that over here. Then the next probability instead is we just did this one. Now you're going to do this one, the probability that they're male. So what's the probability that you select a male? Well, there's 90 males out of 178 people. So it's 90 out of 178. And that probability is 0.506. So we can see that the probabilities are also not the same, which indicates that there's 50% of the population is male, and according to the sample, yet 18% were those with pierced ears. So if they were independent, then it should be the same percentage of males that there are in the population as there are, in any case. Okay, so in this case, we're going to say that the events are not independent. So probabilities are not equal. So events are not independent. Hence, there's a relationship between the gender and whether or not they pierced your ears. All right, that's going to do it for the video, guys. Hope you found this useful and informative. And as usual, I'll see you in the next one.